Hello everyone. Today we are going to discuss the second topic of the rheology. In first topic we have discussed about the Newtonian fluids, and today we are going to discuss about the second type of fluids, that is non-Newtonian. As its name suggests, the system or the fluids that does not follow the Newton law of flow are called non-Newtonian fluids. The fluids for which shear stress is not directly related to rate of shear are called non-Newtonian fluids. Here, if we plot a graph between the shear stress and the rate of shear, we will not achieve a linear line, but a non-linear curve is achieved. So, these systems are called non-Newtonian fluids. Second, the size, shape, and the cohesiveness of the material determine how much force is required to make them move. The consistency curve that are plotted between the shear stress and the rate of shear in case of non-Newtonian fluids are called rheogram, and the non-Newtonian fluids are classified on the basis of rheogram into three categories. First, we are going to discuss about the pseudoplastic flow. What are the pseudoplastic flow and which material are there which follow such type of flow? So, the aqueous system containing natural and synthetic gum, for example, tragacanth, these are called pseudoplastic flow. In case of pseudoplastic flow, when the shear stress is increased, then the viscosity decreases. So, because here the viscosity decreases, these systems are also called as shear thinning system. Because viscosity is decreasing, so we are considering these system as shear thinning system. Pseudoplastic substances start to flow on application of shear stress, and as shear stress increases, the shear rate also increases, but it does not increase in a linear way. What does it mean? It means if we are increasing the rate of shear by a factor of 10, then shear stress will not increase by a factor of 10. But firstly, if we increase the rate of shear by a factor of 10, then shear stress will increase by 8. Then on further increasing the factor of 10, it will increase maybe 7, maybe 10, maybe 11. It means the range on which it is increasing is not constant. It is going to deviate on particular basis. Pseudoplastic flow can be shown by Ostwald-Deckel equation. This equation is Fn is equal to eta prime g. Here n is number given to exponent and it is always greater than 1. So if we can change this equation into the log form, then we will achieve a final equation which is log g is equal to n log f minus log n prime. And if we plot a graph between the rate of shear and the shear stress, this is not linear, but it is further increasing, and then it is also increasing but in a non-linear way. They don't provide yield value, or which is called yield stress. For example, if we take example of pharmaceutical preparation which follow these type of flow are emulsion, dilute polymeric solution, slurry, etc. In further topic, we are going to discuss what is yield value or yield stress. Now, we are going to discuss about the second type of non-Newtonian fluids, that are plastic flow. Plastic flow are the substances which are also called as Bingham body. And if we talk about the example in pharmaceutical preparation, that are flocculated particles in concentrated suspension. In case of flocculated particles, they are held together by weak van der Waals forces, and certain amount of stress must be needed to break up these forces. Only after breaking up of these flocks, these will move. And this force which is needed to break up and then it will start, it is called yield value. Below the yield value, the particle will not start to flow, either stress is applied or not. So we can say, even if by application of force, these particles will not move until they have been broken into smaller ones. The unit of yield value is dyne per centimeter, and the rheogram of plastic flow curve does not pass through the origin. It means they will not start from the point 0. And the equation which is used for such particle is Bingham equation, and that is U is equal to capital F minus small f upon G. Here U is plastic viscosity, F is shearing stress, and G is rate of shear. Calculation of yield value is important in case of pharmacy. Then it is used in pharmaceutical preparation. How the value of yield value is helping to increase the shelf life or biological half-life of the product. First of all, it is helpful to determine the shelf life of the product, and second, it will be easier for the user to use such type of formulation if they have been converted into the smaller ones. For example, if the flocks are available as larger particle, then it is not convenient for the user to apply such formulation or to intake such formulation. It will be convenient by the user only when if these formulation are present in the small formulation form. Yield value is defined as minimum shearing stress that is required for initiating flow. It means it is the minimum stress that must be needed for a material to flow, and the graph between the rate of shear and the shear stress is here. This graph does not start from the point 0, but it starts behind the point 0, and then it goes on increasing, and if we extrapolate this particle, this line, then we will achieve a point that is called yield value, and this point will be helpful to determine the shelf life of the product. The third category of non-Newtonian fluid is dilatant flow. They are also called as shear thinning system due to increased in viscosity at higher shear rate. For example, dispersion containing high concentrated small particles or deflocculated particles, and concentrated slurry of kaolin, that is 12% in water, or if zinc oxide is added in the concentration of 30 in water. Why these particles are called shear thickening system? Because at rest these particles are closely packed and the space which is present between them, that is called void space, is less. So less amount of solvent will be needed to dilute them. But when high shear rate is applied on such system, then particles of these suspensions expand, or we can say they are placed at different positions. Now they are not closer to each other. We can simply show such type of system in these diagrams. Here particles are present, but the distance between such particles are very much higher. They are far away from each other. So dilatant particle can be poured from bottle at low shear stress only. If we shake them high, then it will be difficult for the consumer to take away such formulation from the bottle. The diagram between the shear stress and the rate of shear is represented here. Here, first of all, the viscosity increases and then it decreases. The rate of increasing or decreasing of this type of viscosity is also not linear. So in all the cases of non-Newtonian fluids, we can't achieve a single viscosity from a single graph. So the linear line, if it is achieved, then the type of flow we can simply say is Newtonian. And if the graph or the line is not linear, it is either increasing or decreasing, then the graph or such type of flow will be non-Newtonian. Maybe of any category. We will decide by viewing the graph that it is pseudoplastic, plastic or dilatant. Now the example of Newtonian flow and non-Newtonian flow. Newtonian flow, in this category, various examples which are chloroform, ethyl alcohol and water. And in case of non-Newtonian flow, first we will discuss the example of pseudoplastic flow, that are natural and synthetic gum. All the gums which are of natural origin or of synthetic origins come under the category of pseudoplastic flow. And the example of plastic flow are flocculated particle in the concentrated suspension. And the last one, which are dilatant flow, the example in this category are zinc oxide in the concentration of 30% in water. The meaning of 30% is 30 gram in 100 ml. It means we have to make a solution or a mixture by taking 30 gram zinc oxide in 100 ml water. Then the formulation or the product which we will achieve is called zinc oxide 30% in water. The next topic is thixotropy. Thixotropy means when any formulation changes its form from one to another by shaking it, then it is called thixotropy. If we take example from our daily life, that is mayonnaise. Mayonnaise is a formulation. If we will keep it aside, then it will take a different shape. If we will apply a shear stress, then it will convert into different form. And if we are again keeping it, storing it for further use by not increasing or decreasing its shear stress, then it will finally reaches to its original position. So when these materials are stirred at low shear stress, their viscosity will be high. When these materials are stirred at high shear stress, then their viscosity will be low and their porability will be high. But their viscosity is not directly related to shear stress. It means the graph between the rate of shear and the shear stress is not linear in case of thixotropy. If we are representing the thixotropy of any material, we can't represent a single graph or a linear graph for its position, for its formation of a shape, formation of form from one to another. Thixotropy flow is always reversible. Reversible means first the formulation is of gel type, then it will convert into sol, and then again it will convert into a gel. Thixotropy property has certain significance in the formulation and stability of suspension, for which this property is used in case of pharmacy. At rest, when the shear stress is zero, it means no force is going to be applied on a particular formulation. Then the particle of the suspension behaves like a gel, means their viscosity is high. It makes the formulation stable. And when high shear stress is applied, suspension convert into the sol, make it porable. Only then we can take the formulation out from the container. It is helpful in case of suspension. So in case of suspension, it is highly recommended to shake your formulation before use. It is not necessary to shake the formulation only for changing its form. The changing of form is helpful for the stability, and it is also important to shake because in case of suspension flocks are formed, and these formulations which have higher flocks are not of good use. Such formulation, when finally left aside for further use, for future use, it again convert into a gel form and it increases the shelf life of the product. So we will not conclude from this type of flow that if it has been converted into a sol, then it will not again converted into its original position, original form, that is gel. It is a reversible phenomena. First it is present in a gel form, then it is going to convert into a sol form on applying force, then it will finally convert into a gel form by giving it a higher stability. And this is all about the topic thixotropy. Thanks for watching this video.